Hello learners, welcome to this course on embedded system design using PIC16F877 Microcontroller. In this tutorial, I will be discussing about on how to interface a servo motor with PIC16F877. A servo motor, it is used to get a rotation with great precision. So we can move the servo motor shaft to a particular position more accurately when compared to your stepper motor. Stepper motor also we can achieve a small movement, but here we can achieve with great precision in the sense we have a closed loop system. So closed loop system in the sense we can measure the position of the shaft, and this position of the shaft can be corrected depending upon our input signal. So depending upon the power scheme, whether it is a AC or DC applied to a servo motor, it is called as a DC servo motor or a AC servo motor. So here I have shown a typical servo motor MG90S servo motor. So if you see the internal block diagram of your servo motor, it consists of a DC motor. In order to reduce the speed, a gear connection is attached, so thereby the speed is reduced, and the shaft position is measured using a position sensor or using a potentiometer. We try to measure the shaft position, and this shaft position is compared with the input signal, reference input signal. If there is any deviation between the shaft position and the reference input signal, an error signal will be generated, and this error signal will be used to control the position of your DC motor shaft. So thereby precise positioning can be achieved. So you can see this is a closed loop system. So the motor rotation is achieved and the position of the shaft is measured, and depending upon the shaft position, the correction signal is applied to the DC motor. Thereby it forms a closed loop system. Due to this closed loop system mechanism, precise positioning can be achieved in a servo motor. So if you see the servo motor, it will have three leads. A red lead indicates a supply voltage, brown indicates a ground, and there is an orange line which is a PWM signal. So PWM is nothing but pulse width modulated signal. So pulse width modulation in the sense we can have a square wave and it can have a variation in the duty cycles. So here you see a 50% duty cycle, which means out of the total time period, for the 50% of the time we have on time, and the remaining 50% we have off time. So this is called as a 50% duty cycle square wave. We can also have in a total time period, only for the 10% of the time we have on, and remaining 90% we have off. So this is called as a 10% duty cycle. And the third case, 30% on time and 70% off time. And in the fourth case, 70% on time, 30% off time. So by varying the on time of a square wave, I can change the shaft positions. So for example, here I have a 180-degree movement servo motor. So here we have shown a shaft. If my on time is 600 microsecond, then the shaft moves to minus 90 degree. If my on time is 1500 microsecond, the shaft moves to 0 degree. If my on time is 2400 microsecond, shaft moves to plus 90 degree. So if you see the total 180 degree movement, it requires a deviation of about 1800 microsecond. So 2400 microsecond minus 600 microsecond, which is nothing but 1800 microsecond for 180 degree movement. Then for 1 degree, it will be 1800 divided by 180, which is nothing but 10 microsecond. So for example, let us assume I want to get at 45 degrees. I want to get a movement to minus 45 degrees, which means for 1 degree we have calculated it to be 10 microsecond. Then for 45 degree, it will be 450 microsecond. So this 450 microsecond should be added with your 600 microsecond. Thereby you get 1050 microsecond. So in order for my shaft to move to minus 45 degree, I have to give a on time of 1050 microsecond. And the off time On time plus off time, total we can have about to be 20 milliseconds. On time plus off time, we can have about to be 20 milliseconds. So depending upon my on time, the shaft position is going to vary. So for example, approximately if my on time is 1 millisecond, then the shaft can be along this direction. If it is around 1.5 millisecond, the shaft can move to 90 degrees. If it is approximately 2 millisecond, it can move to 180 degrees. So now let us see how to interface the servo motor with our PIC16F877 microcontroller. So we can connect the servo motor to a port line. So here I am going to use RD0 line, where we are going to generate a PWM signal, and this PWM signal will go to your servo motor, and the servo motor is given with the supply. So for this project, I am going to use MicroC Pro for PIC as an integrated development environment, where we will be writing our embedded C program, convert this program into a hexadecimal file. Then we will be building our circuit in a Proteus 8 professional simulator and try to import that hexadecimal file onto this Proteus 8 professional simulator. So first let us go and build the circuit. Let us go to Proteus 8, create a new project. So first we select a location for our project. So here I will put a folder called as servo motor. Select a folder for storing our project file. Give a name for the project. So name for the project also I am going to give it as servo motor. Press next. Select a schematic. I am going to use a default schematic where we are going to build the circuit. We are not going to use any PCB layout. Press next. No firmware is used. Press next. So only schematic is selected. Finish. So this is the location where we are going to build the circuit. First let us select all the components required for our project. Go to components mode. Pick devices. So I require 16F877 microcontroller. So here you can see 16F877. Double click on it, it will get added to your list. Then I require a servo motor. So here I have a PWM based servo. I am going to take this PWM based servo, 3 terminal. So supply, ground, and the center line will be a PWM signal. Add it to the list. Then I require a crystal. Select it, add it to the list. Capacitors are required. Add it to the list. Then I require a switch for the reset circuit. Select it and add it to the list. Then I require a resistor. Select and add it to the list. So these are the components I require for our project. So after selecting all the components, press OK. So now let me take the microcontroller, place it onto the circuit. Connect the oscillator. I am going to rotate this crystal, place it onto the circuit, and connect the crystal to pin number 13 and pin number 14. Oscillator 1 and oscillator 2 pins. Then connect the capacitors to the oscillator. So one end of the capacitor I connect it to the crystal, other end I connect it to ground. So for connecting ground, go to terminals mode, select ground, press, put it onto the circuit, connect it to the capacitor. I am going to use a 10 MHz crystal, so right click on the component, edit properties, change the value to 10 MHz. And the capacitor value also I am going to change to 33 picofarad. So right click on the component, edit properties, put the value required. So another capacitor also I am going to change it to 33 picofarad. So we have done with the oscillator circuit. Now we have to connect the reset circuit. For connecting the reset circuit, I go to components mode, select the switch. I'm going to rotate it, place it onto the circuit, then resistor, place it onto the circuit, connect one end of the resistor with the switch. Other end of the resistor, I'm going to connect the supply. Other end of the switch, I'm going to connect it to ground. And the intermediate point between your resistor and the switch, I'm going to connect it to the memory clear pin. So this memory clear is an active low signal. So by default, this pin will be at logic high. Whenever I close the switch, the current will directly go to ground. Thereby the terminal will be at 0 volt. Thereby reset will occur. So this completes the reset part. So now we have to connect the PWM signal to the servo motor. So again go to components mode, select the PWM servo motor, place it onto the circuit. So the center line is for your PWM signal. I am going to connect it to RD0. The top line is your supply line. I connect it to supply. And the bottom line is connected to ground. So this is how we interface the servo motor with your PIC microcontroller. So once we have done with the circuit, we can save the circuit. So now let us go and write the C program. Open micro C. So here we create a new project, a standard project. So select a location for storing our project. Give a name for the project. So I will put it as servo underscore motor. Select the device for which programming is required and select the device clock frequency. So here I will set it to 10 MHz. Press next. So we don't have files, so press finish. So this is the location where we are going to write the program. So let us save this program with the name servo underscore motor.c. So now let me open the program. Copy paste it. So here I have declared a function named servo activate. So in the servo activate, I set port D F0, port D 0th pin to be 1 for 600 microsecond. US stands for microsecond. So for 600 microsecond, I am going to make this pin to be 1. And for the remaining 20 milliseconds to 20,000 microsecond is 20 millisecond, I am going to make it as 0. Which means when I have an on time of 600 microsecond, the servo will move to minus 90 degree. So then I change the value RD0 to go to 1 for 1500 microsecond on time, and off time is about 20 milliseconds. So now the servo shaft will move to 0 degrees. And then again I set the on time of 2400 microsecond and off time of 20 millisecond. The servo will move to plus 90 degrees. So here by changing the on time of a pulse, we are going to make a movement of the servo motor shaft. From minus 90, it goes to 0 degree and then to plus 90 degree. So here if you see, I have enclosed this pulse in a for loop. So where I have initialized the I to be an integer value and the I takes a value between I0 to I less than 20. So 20 times we are generating the same pulse. Why? Because the peripheral are slow in nature. The servo motor is slow in nature. So it might miss the change in the signal because here the signal variation is very small for very short time period. Right? So here 1 is for only 600 microsecond. Within that 600 microsecond, the servo motor should be able to recognize it. Since the servo motors are slow, we are going to generate the pulse again and again. For 20 times I am going to generate the pulses. So thereby at least for 3 or 4 times the pulse will be captured by the servo motor and it can move to the particular position after capturing it. If I send only one pulse, there is a chance that the servo motor might miss that signal transition on the line. So in order to avoid that, we send multiple pulses of same duration. Of same 600 microsecond on time, I am going to send 20 number of pulses. So let us assume the servo motor captures the pulse for 5 times. When it captures for the first time, it goes to that particular position. When it captures for the second time, already the shaft is in the desired position, so there is no correction has been taken place. So there is no harm in sending multiple pulses to a slow device, especially the servo motor. So that is why we send multiple pulses to the servo motor to get the servo motor shaft to a particular position. So after declaring this function, I am going to use this function in our main program. So in a main program, first I set trisD equal to 0800, which means we are configuring the port D to be an output port. Then I am just going to call the servo activate function. So thereby it will start moving from minus 90, it goes to 0 degree and then comes to plus 90. Again, since it is in a while loop, again it will go to minus 90, 0, plus 90. So it will keep on continuing. So once we have written the program, let us build the circuit to convert the C program into a hexadecimal file. So once I compile it, an hexadecimal file will be created. Now let us go to the Proteus environment, right click on the microcontroller IC, edit properties, select that hexadecimal file in the program file option. So program file, let me go and select the hexadecimal file. So here you can find X file, servo motor. So this X file, I try to import it into your microcontroller and set the clock frequency to be 10 megahertz. So two things we are doing here. We are importing the hexadecimal file to the microcontroller and setting the clock frequency. Press OK. So now we have put the code onto our microcontroller. Now let us check whether the code is working properly or not. So just by pressing the play button, I can visualize it. So you can see minus 90, it goes to 0 degree, it goes to plus 90. Since it is in a while loop, again it goes to minus 90, it goes to 0 degree and plus 90. So we can see how we can control the shaft position. By changing the on time of a square wave, I can change the shaft position of the servo motor. So in this tutorial, I have discussed about on how to interface a servo motor with PIC16F877. So the servo motor shaft position is controlled by the PWM signal. So we try to generate a PWM signal in the microcontroller, thereby the shaft positioning is controlled. Thanks for watching. Please subscribe for more technical learning. Thank you.